Hello and welcome to this video on virtual condition and functional gauging in GD&T. In this video, we'll be looking at what is the concept of virtual condition, when maximum material condition modifier is applied, how do we calculate virtual condition for an external feature of size like a pin or an internal feature of size like a hole, and what does it mean to have a functional gauge. What do we mean by a functional gauge, and what is the relation between virtual condition and functional gauging? We will see that in this video in depth. So let us first understand the application of this part. So the part which we will be looking at is the blue color part, which is an adapter, basically an adapter which connects a pipe which is shown. That pipe is press fitted to the center hole and it acts as an adapter so that the pipe can be assembled inside this clearance hole on this plate. So basically this is the assembly. The blue color part is being located with respect to its position through this pin. So there is a locating pin, and then there is a fastening hole, and then there is a clearance hole on the pink color part which allows the pipe to pass through. So this is the context, this is the scope. Now let us have a look at the drawing for the blue color part. So this is the GD&T drawing for the blue color part. So it is having a pin, the locating pin. First, let us have a look at the primary datum feature. The primary datum feature is this surface. This mating surface is the primary datum feature. It is having a datum feature qualifier of flatness 0.08. And then this pin, this locating pin, which has a size of 4.9 with a size tolerance of plus or minus 0.1, is datum feature B, which is a feature of size, and that is being controlled with respect to its perpendicularity within a tolerance zone of 0.5 at maximum material condition with respect to datum feature A, which is the primary datum feature, which is this surface. So this feature of size pin is datum feature B, and this hole, which has a size of 5.4 plus or minus 0.1, is the size tolerance. This is being controlled with respect to its position. The position is controlled within a cylindrical tolerance zone of 1 at maximum material condition with respect to A and B. So perpendicularity is being controlled with respect to A, and position is being controlled with respect to B, which is this locating pin. So the position, the basic dimension for position is nothing but 40, which is shown over here. So horizontal dimension is 40, vertical dimension, basic dimension is 0, because they are at the same level. And this is datum feature C, which is again a feature of size, which is a hole. Now this hole, this large hole, is being controlled with respect to its position within a cylindrical tolerance zone of 1 at maximum material condition with respect to datum A, B and C. Datum A, B and C, and the basic dimensions for this hole, which is having a size of 18 and a size tolerance of plus or minus 0.2, are given, which is locating that hole with respect to datum B and datum C, which is this 30 and 20. These two basic dimensions are locating this hole from this hole and this pin, that is B and C, datum B and C. Here the geometrical tolerances are exaggerated to make a point regarding virtual condition and functional gauging. They are not realistic in terms of the parts which are manufactured generally by machining. So machining tolerances are generally lesser, but for the case of understanding of virtual condition, to understand the gaps, we'll take the geometrical tolerances which are exaggerated for demonstration purposes. So this is the drawing for the part. So this pin in the GD&T drawing has been applied with the perpendicularity control, which means that it can vary in its perpendicularity within a tolerance zone of 0.5. So let's say a part is manufactured and the MMC pin meaning that the largest size of the pin turns out to be like this, it is inclined. So MMC pin means that it is at 5 mm, 4.9 plus 1 plus 0.1, which is 5 mm. So the MMC pin turns out to be like this, and it is also inclined by 0.5 mm. That is the maximum perpendicularity deviation it can have at MMC. Now in that case, if we are having a counterpart hole which is size 5 mm, the pin will not assemble because it is having a maximum size of 5, and also it is having perpendicularity deviation on top of that, which is 0.5. So if you try to assemble this pin into a hole which is having a diameter of 5, you will not be able to assemble the pin. You need a larger hole. How large do you need? You need a hole which is larger by at least 0.5 mm extra. So you need 5 plus 0.5 to accommodate the perpendicularity variation along with the size variation or size or the maximum size of the pin. This maximum or minimum envelope which is required for assembly for the hole or for the pin required for assembly of the pin, the minimum size of the hole which is required is 5 plus 0.5. This minimum size of hole required for assembly of the pin considering its perpendicularity variation and its size variation is nothing but virtual condition of the pin in this case. So the hole size, minimum hole size required is the virtual condition of the pin, which is 5 plus 0.5. This is 5.5 mm. So this is called as the virtual condition of the pin. Now let us have a look at this hole, this fastening hole, which is having a size of 5.4 plus or minus 0.1. It is being controlled with respect to its position with respect to datum feature B, which is the pin, within a cylindrical tolerance zone of 1 at maximum material condition, and these are the basic dimensions, which is 40. Now the position of the hole is being controlled with respect to this feature control frame. Now if we consider the smallest possible hole, the smallest possible hole will be 5.4 minus 0.1, which is 5.3. Consider this as the smallest possible hole. This smallest possible hole can deviate in its position as shown. It can shift to the right, it can shift upwards, or it can shift towards the left, or it can shift towards down, or it can shift all around with respect to a cylindrical tolerance zone of 1 mm. So this is an envelope which is being created, which is basically because of the positional deviation of the hole. Now you can see that there is a smaller envelope inside. So if we are trying to assemble a pin, so this is the smallest hole. If you are trying to assemble a pin into the hole, when that pin is at true position, then the largest size of the pin which will be required to assemble into the hole, which is deviating to its maximum in terms of its position and size, that pin has to be the size of 5.3 minus 1. So basically the hole, a smallest hole at maximum material condition, because the hole at maximum material condition is the smallest one. The smallest hole, when it is deviating in its position, it will have an envelope, an inside envelope, which is basically the largest size of the pin which can be assembled into the hole considering its positional deviations at maximum material condition. That size of the pin, the largest size of the pin which can be assembled into that hole at true position, is nothing but the virtual condition. So the virtual condition of this hole on the drawing is 4.3 mm. That is 5.3, that is the MMC size of the hole, 5.4 minus 0.1, 5.3 minus the geometrical or positional control tolerance, that is 1 mm. 5.3 minus 1, 4.3 is the largest size of the pin which can be inserted into a hole when it is deviating to its max at maximum material condition, which is nothing but virtual condition of the hole. Similarly, we can do the same calculation for the larger hole, this hole over here, the 18 mm one. That hole also, considering that the red color line indicates the smallest possible hole, which is 18 minus 0.2, deviating to its max in terms of its position. It can move towards left, towards right, towards up, towards down, all around in a cylindrical tolerance zone of 1 mm. Considering the maximum deviation, we will have an inside envelope as shown, which is the size of 17.8 minus 1, which is MMC size of the hole minus the geometrical control, which is positional control tolerance, which is applied, that is 1. 17.8 minus 1, which is 16.7 mm. So the inside envelope is 16.7 mm, which is nothing but the virtual condition, which is the largest size of the pin which can be assembled into the hole, considering that the hole is deviating to its max in terms of position and size. So the virtual condition of the center hole is 17.8 minus 1, which is 16.7 mm. Now let us have a look at the functional gauging of this component. Now this component, what do we mean by functional gauge? A functional gauge is basically a gauge block or a device or inspection method which is used to verify the assembly of components which are being manufactured. So you have parts which are being manufactured, you just assemble those parts with the gauge block and verify whether they are assembling or not. If they assemble, then the part is okay. If they don't assemble, then the part is not okay. That's basically a gauge block, a functional gauge block. These are very commonly used for parts which are required to assemble into the assemblies, and verifying that assembly is easy using a gauge block instead of always measuring the dimension using vernier caliper or other inspection methods. So gauge blocks are a quick way of checking or verifying whether the part will assemble in its use case or not. So that gauge block is designed based on the concept of virtual condition. We will see how. So for this part, the gauge blocks are based on the feature control frames which are being applied. So the feature control frames which have been used, there are 3 feature control frames. So in the GD&T drawing, there are 3 major feature control frames for which we need to design for the functional gauging blocks. So this is first, this is a perpendicularity control. So the corresponding functional gauge will be, it will be nothing but a gauge block which is contacting the datum feature A, which is this surface, and it is having a hole which is through which the pin will pass through, and the size of this hole is nothing but the virtual condition which we calculated. So that gauge block will have the size of the hole same as the virtual condition in gauge tolerance, and it will contact the datum feature A, which is this surface. So this surface of the gauge block, gray color gauge block, is the datum feature simulator for datum feature A, and the hole is at the virtual condition. So you can see over here, this is the gauge block for the first feature control frame. This is the gauge block for the first feature control. Now for the second feature control frame, the gauge block will have a centering hole, which is basically having a mechanism for centering of the pin with respect to the hole. So basically what this means is that the position of this hole is irrespective of the size of the datum feature B. So whatever the size of the pin, the hole should be centered with respect to that size. So if we don't have these centering mechanisms, then there will be a gap between the hole and the pin, and that will cause datum shift. So to avoid datum shift, we have these expanding mechanisms so that it will centering mechanism which is allowing the pin to be centered as per the hole. So the gauge block will include this centering mechanism which will center the hole as per the pin, and on the other side there will be a pin. So there will be a pin. Again, note that this surface, the datum feature simulator for A, is in contact with datum feature A. That is the gauge block, the gray color gauge block is in contact with the blue color part at datum feature A first. So that is maintained. Additionally, there is a pin, and that pin on the gauge block is at the size of the virtual condition of this hole, which we had calculated. So the size of this pin is the virtual condition of the hole, which is 5.3 minus 1, which is 4.3. So size of the pin will be 4.3. So this gauge block is corresponding to this feature control frame. So there are 2 gauge blocks. One gauge block was earlier, one was for perpendicularity. Second gauge block is for this position control. And then there is a final gauge block for the center hole. So this gauge block will have a hole the size of the virtual condition of the hole on the blue color part, and also it will have centering mechanisms for the pin as well as the hole. So centering mechanism for the pin and centering mechanism for the hole, because here irrespective of the size of B and C, which are features of size, the position is being controlled. Hence, whatever the size of the hole and the pin have to be centered with respect to their counterparts. So there should be a centering mechanism for the hole as well. So here the centering mechanism will be incorporated along with the pin, which will center the hole on the part with respect to the pin on the gauge block. So centering mechanism over here, which is indicating this B and C. A is already in contact, and then at the true position the pin is inserted. So this pin is inserted at a true position after locating the part with respect to item B and C. So when this pin is inserted, it should go through the part and assemble cleanly. That's the requirement. So this gauge block is for this feature control frame. So you can see there are 3 gauge blocks here. 1 gauge block for perpendicularity control, 1 gauge block for position control, and 1 gauge block for this final control. So this is the final gauge block. This pin is inserted, and if the pin goes through, the part is okay in terms of its assembly. So the final gauge block, in order to verify the position of this center hole and make sure that it assembles with its counterpart and has the required clearance with the plate, this is the gauge block. As you can see, the size of this hole, diameter of the hole, is virtual condition of the feature control frame number 1, which is perpendicularity. The size of this pin is virtual condition of feature control frame number 2, which is a hole. So the size of this pin is that on the gauge block, and the size of the pin on the gauge block is virtual condition of the feature control frame number 3, which is also a hole.